obviously when we talk about systems, we talk about power systems. So let's go ahead and give me my highlighter. Okay, so the power system, Karen, have to be protected from a major thing. Every time you have a power system, guys, we're going to be protecting them from short circuit and ground fault. And you're looking at the thing that protects them from short circuit and ground fault. Circuit breakers and fuses. Always to protect the equipment as well as the material. So, system protection. A couple of things about system protection, guys. Identify devices, users, devices that we can use for system protection, which is basically fuse and circuit breakers. We will talk, guys, about the circuit breakers as part of the overcurrent protection device, the fuses, and something called ground fault protection devices. Ground fault protection. So these are the three things that we use to protect from overcurrent. You guys are familiar with the term overcurrent, right? Overcurrent can be ground fault, can be short circuit, can be overload. So we have the circuit breaker and the fuses to protect us from overcurrent protection device. A proper adjustment for the devices with adjustable elements. We'll talk about adjustable circuit breakers. At the end of this class, guys, we will be doing short circuit analysis like we did in the last project. I think, Matt, did you do the short circuit analysis and coordination last time? And we will have an adjustable circuit breakers. And adjustable circuit breakers, these are non-adjustable. You're looking at them, right? They are adjustable circuit breakers. We can tweak them. Talk about this. Selective coordination. Like we did in the commercial project, guys, we will do an overcurrent protection, short circuit calculation, and overcurrent protection coordination for this particular project. So this is just a few requirements. Ground fault protection, guys. In the power system, Karen, there are 28120, there's 48277, there's 600 volt, some voltages, 24120. All these systems, guys, are different voltages, different vehicles of delivering power to the equipment. If your voltage, the NEC code would require you, if your system, here's the system. If your system is 1000 amp or more, and the voltage is 480/277, which meets this criteria, you are to provide a ground fault protection, a special function in the circuit breaker, right here, ground fault protection, special function with the circuit breakers, that looks at the ground fault only. The reason that they do it this way, guys, on major electrical equipment, because if you have 1000 amp 482/77, the ground fault is so high that could be very destructive, but that cannot be sensed by the circuit breaker. So you could have 700 amp ground fault sitting on your system, burning your building, and the circuit breaker sitting there doing nothing. So what they do, Karen, is they have a specially designed function or device that can be installed in the circuit breaker or separate, that looks at the ground fault, the current that coming out of the phases, coming back on the neutral, and if there's substantial difference between the two, it will trip. So the only thing you need to understand, guys, is required on a system 482/77, more than 150 to ground. So it's not required in 240. So if you have a system like 208, you have a 208 or 240, these system is not required for that. It's only required on 482/77 system. Any comments, guys, about the ground fault? Looks only at the ground fault. You'll see a picture of that one in a second. So that's the ground fault protection. For feeders and branch circuits for services, so required on services and feeders, and also recommended branch circuits and feeders. Here's the requirement for this one, like 1000 amp or 150. You don't have to put it in a place where a shutdown can increase. So if you're cooking chemicals, it's not required in a place where a circuit breaker, guys, that tied to cooking some chemicals. If you trip the circuit breaker, you could create more hazard. Does that make sense? More hazard. So they don't want you to put it in a place where tripping the circuit breaker will create more hazard than a ground fault. Does that make sense? You see this one all the way, non-orderly shutdown. So nuclear plants, chemical plants, anything that any circuit or any branch circuit or feeder that feeds very sensitive equipment, and if you don't shut it down orderly, you're going to create more hazard. It's not required to put the ground fault protection in it. Ground fault protection. Okay, so that's what you have, guys. You have a circuit. You have here's my main circuit breakers. I have a fuse disconnect overload on a feeder. So if this circuit breaker is 1,000 amp and the voltage is 480/277, I am required to have a ground fault protection for equipment on this circuit breaker. So if I have a ground fault right in here on this system, anywhere in this system, that could be sensed and trip the circuit breaker on ground fault. So when I was your age, guys, and we talked about ground fault, it confused the crap out of me. The reason why ground fault and short circuit, you take phase A to the ground, right? Or phase A to the ground, that's a ground fault, right? What's the difference between ground fault and short circuit? Short circuit is phase to phase to phase, that's short circuit, or phase to phase. Ground fault, any phase to the ground is a ground fault. What's the difference in terms of value? The short circuit is much higher than the ground fault typically. That's all. Here's how the ground fault sense, guys. Very simple. Look at this. Here's my phase ABC. So I have, suppose, look what happened. Suppose I have a ground fault in the system. So I have 100 amp here, 100 amp here, and I have, let's just say here, I have 80 amps. Can you guys see that? This phase has an 80 amps. And then the neutral, you have to do your math. The neutral is going to be carrying current. Say I have 20 amps in the neutral. Okay. So what this device looks at, Karen, is it looks at the current in each one of them, does the math on it, and if they don't add up, which I don't know if they will add up, so you take the neutral, I neutral. If you guys remember how you do that one long time, you take the A squared plus B squared plus C squared minus 2AB minus 2BC minus 2CA. These are all the currents. These are the currents in each one of them. If they do this math and it doesn't add up, guess where the current went? Karen, the current went, it went right here to a ground fault. There's a ground fault system. So no magic. They sense the current that's going, guys, through every phase. They do the math electronically. And if there's substantial amount of difference between the neutral current and the three-phase current, it will trip the circuit breaker because you have a ground fault. Okay, so that's basically what the ground fault is. The only thing you need to know, guys, is required on 1,000 amp or more. So, Adam, we have our services and feeders and branch circuits to be. Now we have the building that we have, guys, is 4,000 amp. So in a 4,000 amp building, you are required to put a ground fault protection, one ground fault protection. Moving into the second circuit breaker, guys, is which is the second overcurrent protection device, the circuit breakers. Karen, the circuit breakers are made in air or oil or vacuum. So you guys are looking right here. Can you guys see that? That big boy? This is an air circuit breaker. What is an air circuit breaker? You have contacts, guys. When you open the contacts, you open them in the air. So there's arc. You're looking at a big fat boy right here. This is also a 3,000 amp circuit breaker. This is an air circuit breaker because when they open them, there's no vacuum tube, there is no oil inside it, so it's an air circuit breaker. So almost all the stuff that you guys are going to be doing probably going to be an air circuit breaker. Either molded case like this or power circuit breaker like this boy, air circuit breakers. Now what the heck is oil? The oil circuit breaker, guys, what they do is they put the contacts, they immerse them in oil. When they open, it extinguishes the arc. That's an oil circuit breaker. They use it in utilities, Adam, in high voltage. A lot oil circuit breaker is a tank full of oil. You're going to see in a second. They open everything on the oil. What is a vacuum circuit breaker? They have a tube, guys, a little tube and contacts inside it, and they remove the air from it, so it's vacuum now. So when you open these contacts, you don't arc that much. The whole idea, guys, the reason why we have these three types, to get rid of the arc. Every time you open a circuit, you create a huge arc that over time, it will damage the equipment. So the bigger the equipment, the more that you need means of extinguishing the arc. So that think of these air, oil, or vacuum. So typically, guys, most 99% of the time, you're going to be dealing in your career with air circuit breakers. Okay, so that's how they build them. Then of course, there's thermal circuit breakers. And electromagnetic circuit breakers, thermal, they are operating by heat. Heater, so there's a heater, there's a bimetallic strip closer to bimetallic strip. It heats them and it will trip mechanism. They expand at a different rate and it will trip. And you can initiate a delay, of course, on these circuit breakers. So the major type of circuit breakers, Karen, are air, oil, or vacuum. The tripping mechanism of circuit breakers can be the following. Can be thermal, which is basically a heater. You're going to see it in a second here. Here's how the thermal, guys, thermal circuit breakers, it's called thermal because you have, here's my load, you have a heater here. The current goes right through this heater and it heats it. If it goes higher than, say if this circuit breaker is supposed to be at 20 amps, and now we're pulling 30 amps out of it, 30 amps, it will heat this heater, create heat, and this heat will heat that bimetallic strip, and the bimetallic strip will pull this one to open. It will interrupt that circuit. Any comments, guys, about thermal circuit breakers? They call them thermal circuit breakers, like the overload. They work on heat. They work on heat. The second one, guys, and this is the symbol that they use for it. It's a symbol of an overload. You heat an element to trip the circuit breakers. All this is, Adam, is just how this works. This is a thermomagnetic circuit breakers. It has two components, thermal and magnetic. Thermal circuit breakers only, thermal circuit breakers only. Typically, guys, we don't have them thermal only. We have them thermomagnetic. So here's my thermal overload. The second part is called the magnetic circuit breakers, the tripping mechanism. This guy senses the current by connecting a coil in series with the load. A coil in series with the load. It is called an instantaneous strip circuit breakers based on these tables. It has the maximum rating. And most of circuit breakers, Adam, actually has two components. And you guys heard it all the time. It's called thermomagnetic circuit breaker. Employ both thermal and magnetic. Thermal and magnetic. So when you hear, Karen, a thermomagnetic circuit breaker, it has a heater that heats if you have an overload and trip. And it has a coil that trips a contact if you have a short circuit. That's a thermomagnetic. Adam, you're looking at a thermomagnetic circuit breaker right here. That's called the thermomagnetic circuit breaker. So there's thermal, there's magnetic, and there's a combo of the both, that thermomagnetic circuit breaker. Combo of the both, thermomagnetic. Okay, Karen, there's some coil. Here's the magnetic circuit breaker. The way this guy works, if this is a 20 amp, gentlemen, and you have a short circuit right here, a ground fault, going to the ground. So now you're pulling out of a 20 amp, say, let's just say 300 amp momentarily. Can you guys see that? You're pulling 300 amps. Now the current is going to go through the coils, right? Create a magnetic, when it goes through the coils, it's going to create a magnetic field that pushes this solenoid arm that moves the solenoid arm away and open the circuit breaker. So they open it based on like magnetic starter, guys, a coil. It energizes the coil, and the coil have a plunger or soil arm, and then pushes these contacts to open. So they use magnetism as a means of opening the circuit breaker instead of thermal. Magnetism. Does that make sense? Can you guys see how you energize the coil? It creates a magnetic force, pushes these contacts open. That's what happened inside Adam, inside that bit, if you have a short circuit. If you have a ground fault, there's a heating element that slowly, gently heat these bimetallic materials and trip. Any comments, gentlemen, any questions about the magnetic component of a circuit breaker? So Karen, when we say instantaneous strip circuit breaker, this is what they have. They have in the field, when you guys go, I know one day you'll be specifying circuit breakers and say, somebody will say instantaneous strip circuit breaker. What the heck is that? That's a magnetic circuit breaker. It just has magnetic in it. It looks at short circuit. Short circuit, that's all. It doesn't look at overload. And it looks something like this. Okay, so this is how the symbol that they use, guys, for magnetic circuit breakers or instantaneous circuit breakers that they use, different application. Now, Karen, the 90% of the time, guys, 90% of the time, I want to put 90% of the time, your circuit breaker will have dual component. This is called the thermal and magnetic, thermomagnetic circuit breaker. Can I have thumbs up, Chad? We know why thermomagnetic. It has a coil that trips on short circuit and a resistor that heats bimetallic material. that trips based on overload. Everybody understand that one? So this component here, guys, provide overload, and this component short circuit and ground fault. Cool? So that's, Karen, you're looking at thermomagnetic circuit breaker right here in my hand. Thermomagnetic circuit breaker. Any comments, guys? Any questions about thermomagnetic? That's where the term came, thermo. It depends on heat as well as magnetism to trip the circuit breaker. So the heat, this is a trip by heat. This is a trip by magnetic force. Don't you guys get amazed how somebody have thought of this? Doesn't amaze you that somebody have thought of all these technologies to protect the power system? Your power system, Karen, without circuit breaker is completely worthless. Completely worthless. It's like having a car. Imagine, Adam, driving your car without brakes. How good is a car that you can drive without brakes? These are the brakes of the power system. If you don't have a brakes, your car is worthless. Literally, right? So these are the brakes of the power system. Okay. Circuit breakers as well as fuses, guys, have two ratings. One of them is called the trip rating. This is, say, a 20 amp circuit breaker that's tripped the amount of current that should cause the circuit breaker to open its contacts when it's exceeded. So if you have a 20 amp circuit breaker, guys, that's called the trip rating. The interrupting rating, gentlemen, is the amount of the maximum amount of current that the circuit breaker can trip under abnormal condition like short circuit or ground fault. So Adam, that 20 amp circuit breaker that you have right here has a 20 amp circuit breaker as well as 10,000 amp. So the interrupting rating, gentlemen, is this, and the trip rating is this. So trip rating, that's how it's rated for continuously. And the interrupting rating is the amount of current that this circuit breaker can safely interrupt under abnormal condition like a ground fault and short circuit. Any comments, guys, about these two values? Here's another, so you can have a 2000 amp and the interrupting rating for this guy, say 65,000 amp. That's how much short circuit this circuit breaker can handle. Comments, guys, about the interrupting rating versus the trip rating, interrupting trip. Cool. So that's interrupting and trip. Shunt trip. What they do sometimes, Karen, they have wires coming out of this circuit breaker. Look at this, guys. You have wires coming out of this circuit breaker, and these wires, you can put a voltage across them, and you can remotely trip the circuit breaker. So shunt trip, a small solenoid that you can energize. Here's my circuit breaker coming in here. Here's two wires coming out of it. You can put 120 volt right here and trip this circuit breaker. Open this circuit breaker. Okay. Open the circuit breaker contacts by energizing the solenoid externally. That's what a circuit breaker is, a shunt trip. If you hear, Karen, two applications that require shunt trip, guys, air handling unit require a shunt trip on it. If you have a fire alarm, if you have fire alarm condition, you need to trip the circuit breaker that feeds the air handling unit, number one. And also, guys, in the computer room, Adam, all these data centers, you have to have an emergency power off, EPO they call it. EPO button, when you push it, it will shut down all the crack units, the cooling units, the PDUs, and the UPS system have to be shut down with some differences. So it has to be shut down upon the existence of a fire. That's your shunt trip. Auxiliary switches, all circuit breakers, guys, come with contacts, normally open and normally closed contacts, especially the power circuit breakers. Micro limit switches, these guys are used to send signal. So if I want, this one doesn't have it, but this guy has it. If I want to know every time the circuit breaker is on and off, I can wire to a contact that will send the signal to my iPhone, literally, to my iPhone that my circuit breaker is on or off. So they capture these contacts, they take a signal from a contact, guys, they interface it with a control circuit, and it gives you the status of your circuit breaker. You can illuminate a light, an indicating light, so every time the circuit breaker is off, you got a red light. Every time the circuit breaker is on, you got a green light. Any comments, guys, about the shunt trip and auxiliary switch? Auxiliary switch or contacts, these are signals. You send the signals every time the circuit breaker is on and off. Shunt trip, you remotely trip the circuit breaker. You remotely trip the circuit breaker. Karen, here's what shunted trip looks like. Suppose that I want to put a thermostat, guys, right here that trip the circuit breaker if the temperature read 100°F. If I want to set the circuit breaker to trip, guys, if the temperature in this area reach 100°F, I put a thermostat right here, and I bring, so this is a line to, let's just say 24 volt DC, 24 volt DC, or 120 AC or DC. You put it into the thermostat will close, energize this coil, and this coil will open, the shunt trip will open the circuit breaker if the temperature is to reach a predetermined value. Any comments, guys? Any questions about the shunt trip? Shunt trip. You're going to hear this one all the time, Matt and Adam. When you go to Mishad Kul and you become a project manager and you lead your own project, you're going to hear shunt trip. Hopefully you remember, Chad, one day talk about shunt trip. Big deal, you know. So did you guys hear it now? The shunt trip, just a little coil, you energize to trip remotely the circuit breaker before predetermined value. Auxiliary switches or contacts, guys, these are used to give you an indication light. So you can bring a 120 volt here, and you put a light, and you take it from here. Here's my neutral, here's my hot. So what happened is every time the circuit breaker closes, it will close this one, and my green light is on. So that's how they do auxiliary. They get you these contacts, guys, give you the status of the circuit breaker. They give you the status of your circuit breaker. Any comments, gentlemen, about auxiliary contacts or switches and shunt trip? Very, very important. This big boy, Adam, has tons of auxiliary contacts and shunt trips that you can remotely trip. You can push your iPhone and turn this on and off from your iPhone. That's through the auxiliary contacts and so forth. So big deal with bigger. Okay, air circuit breakers. Moving, so that's how that tripping is. The tripping mechanism in any circuit breaker, we talked about thermal, we talked about magnetic. There's also electronic, guys, where you can sense the current electronically and make a decision. That's called electronic circuit breakers. Adam, you're looking at thermal circuit breaker right here, and that circuit breaker right at the top of it, guys, right here, is actually an electronic circuit breaker. Can you see that adjustable? This electronic circuit that adjusts. You can adjust it. So electromagnetic circuit, thermomagnetic circuit breakers, and electronic circuit breakers. Okay, air circuit breakers. Air circuit breakers is the way they design the circuit breaker, guys. The most common one is called air circuit breakers. The medium, the insulating medium to break the arc. The arc is the air. So these contacts are sitting up in the air, guys. When you open and close them, you open them and close them in the air. There's a couple of types, guys. There's molded case circuit breakers, I think probably 2500 amp. You can get them up to different voltages. Low voltage power circuit breakers, you're talking about 800 amp all the way to 5000 amp. This one is from 15 amp to 2500 amp. Medium voltage circuit breakers, the same thing, probably from 800 amp to 4000 amp or so. So these are the air circuit breakers that you can handle. Adam, most of the time you guys are going to be molded case circuit breaker or power circuit breakers. Molded case circuit breakers, can I get you guys to look at? Here's a molded case circuit breaker. That's the first one. Power circuit breaker, it's sitting right at the top of it. That's called power circuit breaker. Do you see the difference? Bigger, more robust, more expensive. One of these will cost you $10,000 versus $1,000. Medium voltage circuit breaker, the only difference is they use it on 5K volt, 15K volt, 25K volt, 35K volt, or something similar to this. They use them in a higher voltage. When you open the contacts, guys, you always have an arc, and the arc has a lot of heat that need to be dissipated. So designing all these circuit breakers will be different. The way they design them to get rid of all this arc and all this heat. So here's what happens, Anna, when you have a short circuit and you open the contacts. There will be a huge amount of arc coming in this. And getting rid of this arc, guys, become the job of the designers of circuit breakers. If you don't get rid of this arc fast, your circuit breaker is going to open and it's going to melt in the process. So they have different ways of getting rid of this arc when they open the circuit breaker. Big deal. You'll see them in a second. Okay, molded case circuit breaker, guys, typically low voltage. You're looking at them like here, 600 volt or less. Low current circuits, so typically from 15 amps, like I said, to typically 2500 amp or something like this. You can use them for lights and appliances and small circuit. That's exactly what you guys have been doing with me. These are called molded case circuit breakers. Okay, splitter use of higher voltages, metal or insulated plates on top of contacts. They have okay, so they use something called a splitter and arc shoes. I don't know if we have them here. Oh, look at that one. They use metal or insulated plates on top of the contacts, permit hot gases to escape, but lengthens the arc path cooling effect. So to get rid of the arc, guys, they have a splitter. Maybe I should go into the splitter here. I don't have a picture of it. Let's go look at the splitter that they use. We talked about the thermal guys. Okay, all this. Thought I have a place where we can use contact. Here's the arc. Can you guys see the arc here? Now they have splitters. What they do, Adam, is they put these splitters right here, and then it allows the arc to go right in here, guys, and extend the arc up a little bit and split it. Believe it or not, putting these splitters here inside the circuit breaker will help the circuit breaker handle the arc. Will help the circuit breaker handle the arc. So these are, can you guys see the arc splitter contacts right in here? It allows, so long story short, you guys probably don't need to know that one, but it will help the circuit breaker extinguish the arc that's coming out of interrupting of a circuit. The second technology that they have is they have something called arc horns. Can you guys see the arc horns? That when you open it, channels the arc away, and it takes it into these splitters, so you can chop that arc. So that's my my splitters, a means of getting rid of the arc, Any comments, gentlemen? Any questions, comments? So a splitter, why do we use them? They typically don't ask you guys. Inside, built into the circuit breaker, these splitters and arc horns. Okay, low voltage power circuit breakers. Low voltage power circuit breakers, Adam, you're looking at them right there, big boys. They have main contacts, connect the line and load. If you guys look at the back of them, they'll have contacts that connect the line. They're not like torqued to it, they're plugged in. Arcing contacts direct the arc away. They have arcing contacts that take the arc away from the main contacts. So when it comes to circuit breaker design, guys, I can't emphasize this enough. It's all about getting rid of the arc safely. So they add different contacts to get rid of the arc, so you don't burn the contacts that are carrying the arc under normal condition. They have arc horn. Look at these. They're called arc horn aids in drawing the arc away from the arcing contacts. Also helps stretch the arc away. So these horns, guys, like you saw, it will move the arc away from it, so it will facilitate the extinguishing of this arc. The single most important thing, guys, when it comes to circuit breaker is how do you extinguish the arc that's coming out of interrupting a short circuit or ground fault or an overload condition. Medium voltage circuit breakers, guys, they are used on higher voltages like 15K. Blowout coils, they have something called blowout coils again, a means of distinguishing, are connected in series with the arcing contacts. So arcing contacts, current flows through them when the main contacts are open, so it moves the arc away from the main contacts. Power construct by attaching a small piston to the operating lever of the breaker. So this is a mechanism, guys, that they use to diverge the arc away from the contacts. Diverge the arc away from the contacts. Okay, when you go to the oil circuit breakers, very easy, Adam. They put the dielectric oil and they put the contacts right into them. They put so tank is at a ground potential, insulated from the live parts, and they put an oil in it. low oil or oil poor type. They have different type of construction that they use, guys. Vented type, double brake type, plain brake type. All these guys are oil circuit breakers. The only time you're going to see oil circuit breakers if you're dealing with high voltage. What's an oil circuit breaker, guys? A tank like this with contacts inside it full of oil. When you open the contacts immersed in oil. So what happens if you have oil? The oil will extinguish the arc. Great arc interruption. Can I get you guys to understand that one? This is not an oil circuit breaker. If you go open that sucker, there is nothing in it. This is an air circuit breaker. Different tanks, you have to have a tank. The last thing and the most expensive one, guys, and the better one is called vacuum circuit breaker. Matt, they have a tube like this. They have a process of removing the air from the tube. And inside it, they have contacts that they open and close. So when you open and close with no air inside, you have no arc or very, very limited amount of arc. That's it. If you have no arc, guys, then you can make the circuit breaker interrupt the circuit and live to fight another life. The key point of our circuit breaker, guys, if you interrupt the short circuit, do you want to reset them and move on? Or do you want to replace them? If you want to replace them, might as well put a fuse, right? Fuse, open, replace it. That's why when it comes to circuit breaker, it's a big deal. They need to live to fight another day after they interrupt. So contacts inside sealed enclosure. Perfect vacuum is impossible, but get very close. Still very, very few particles of air still. But it minimizes, guys, lift in the chamber. Any arc produced will be extremely small. So because of very, very small amount of air in the chamber, you can have the arc very, very small. A half to 3/4 of an inch clearance between the contacts. So it gets you a smaller circuit breakers, guys, with smaller contacts. Between the contacts required control voltages over. So they use them a lot in high voltage as well as in low voltage too. So for very little maintenance, no little maintenance. There is no little maintenance like an oil. If you have an oil circuit breaker, guys, what happened with oil? Oil spill, pressure, dielectric test, and bunch of other things to make it work. Okay. Summarize, we have air that you guys are going to be dealing with all the time, air circuit breakers. We have oil circuit breakers and vacuum circuit breakers that we'll be probably dealing with a medium voltage. Any comments, guys? Any questions about circuit breakers? Any comments, any questions before we talk a little bit about the curves, their curves? So we talked about this one, guys. Let me erase this one. I have a couple of pictures to show you. You're probably thinking Chad is nuts here with all the circuit breakers. You guys want to hear this one all the time. We talked about the arc, extinguishing the arc, the splitters. Here's the arc contacts, the arc contact, the arc splitters, they remove them away from the main contacts. Here's another way of horns, Adam, where you channel the arc away from the contacts. So you can go to the splitter and split them, extending them. It cools down. It helps opening the contacts. Here's what happened when the circuit breaker interrupt, guys. The arc is drawn away, and instead of arcing here, guys, it arcs right here. So you move it away from the main contacts. So who cares? Your contacts will live longer. Your contacts will live longer. Here's oil circuit breaker, guys, with different arc truth and main contacts and what's not, how they open inside the arc. This guy is called typical dead tank oil contacts, and you probably, guys, a few of you will ever be dealing with this. Can you guys see where the contacts that they open it right here inside the oil? There's an oil here, operator linkage, and there's oil inside it. So you can manually open and close this circuit breaker. Here's another oil, guys, the way they open these contacts. Look at that one. When you open this contact, it funnels all this energy outside, away. So these are all different type of, I think this is called plain brake low oil tank. Typical vented type low. This is called your vented type low. So these are all different circuit breakers. This is your typical double brake low. Can you guys see you have double contacts to open them? And the last one, gentlemen, is the vacuum. You can see, guys, inside this cylinder, there is no air or very limited amount of air, and you're interrupting the contacts right here. And in air, so very, very limited amount of arc will be there. So the contacts will live longer. Your contacts will live longer. Okay, so that's basically the contacts. Any comments, guys? Any questions before I move and just talk a few more seconds about the overcome protection device for the curves, the tripping curves? To summarize, guys, your circuit breakers are made out of oil, air, and vacuum. You will be dealing 90% of the time with air. The air ones are called molded case circuit breaker, insulated case circuit breakers, as well as power circuit breakers, and medium voltage circuit breakers, the oil ones. The air ones. The oil ones, guys, have different type of design. The vacuum ones are typically for medium voltage and so forth. Any comments, gentlemen, any questions, and ladies, about circuit breakers? Ground fault? Okay, now, Matt, if you remember, in the commercial project, what we did, we have time current characteristic curve. Every curve, guys, or circuit breaker has something called time current characteristic curve. This time current characteristic curve will decide how fast the circuit breaker will trip, how fast my circuit breaker will trip, and I'll show you in a second here. So the higher the current, the faster the circuit breaker will trip. The higher the current, the faster the circuit breaker will trip. You can see the faster the circuit breaker will trip, and that's called the time. You can see the curve here. This is your overload condition here. This is your short circuit condition, and in between is the melting or the opening contacts for this characteristic, for this time current characteristic curve. We'll look at this one, guys, in a second in a better view. If you have a circuit breaker atom, they are supposed to open within 3 cycles. So here's 1 cycle, 2 cycles, and 3 cycles. They're supposed to open within 3 cycles. And 3 cycles, Karen, is 1/20th of a second, right? You take a 3 cycle, guys, divided by 60 seconds, that'll get you 1/20th of a second, right? 1/20th of a second. If you have a circuit breaker, it's supposed to open 1/20th of a second. If it doesn't, your equipment will burn. Most of the equipment, guys, will burn. So that's the opening characteristics. If you have a fuse, the same thing, guys. The fuse have also a current, time current characteristic curve that looks something like this from the point it starts melting to the point it's completely over the circuit. The higher the current encountered by the circuit breaker, the faster the circuit breaker will open. The faster the circuit breaker will open. Adam, the same thing for ground fault, guys. They have also a curve that you can set them up. You can set your ground fault if you have 1,000 amp or more. You can't set them at more than 1,200. Is it 1,200 amp, I believe? More than 1,200 amp. So, but you can adjust and delay that. Look at that. This trips at 0.1. This trips at 0.5 to coordinate between the two. There's something called, guys, with the current characteristic curve. This is probably the second time we talked about current characteristic curve. You guys, in a couple of weeks, you're going to hear your friend Chad standing here and using SKM PTW to do this. Coordination. When you do overcomputation coordination, guys, if Karen is to go right now and short one of these lights above your head, Karen, you want the circuit breaker in this panel right in this room to trip not the main 3,000 amp fuse in the basement. That's what a coordination is. How do you achieve the coordination? Accomplished easily by using fuses alone, or you can use it by fusing with circuit breakers. Here's a few things you have to keep into consideration, guys. Proper selection of protective device. So the right protective device, correct size of various components, like the withstand rating of the components, adjustment of the overcurrent protection device, adjusting them. So that's how you can get a fully coordinated, and you have to run the full coordination of these circuit breakers and adjust their tripping mechanism. Proper maintenance of devices after place, and then after you install the system, of course, you have to properly maintain the system. Maintenance is a big deal to maintain the coordination. So Karen, like I said, in a couple of weeks, guys, you're going to be doing coordination for this 4,000 amps switch gear and all the panels that we have. What's the coordination? What does the coordination mean when you guys leave here and somebody asks you if you have a short circuit or a ground fault in one fixture, the circuit breaker feeding that fixture will trip and everything else stays the same. No interruption in the power other than the branch circuit that has a short circuit or ground fault. So that's your coordination. So that's basically it, guys, in terms of circuit breaker, air, oil, vacuum, fuses, ground fault. I'm going to show you just a couple of pictures here. So here's the current characteristic curve. Ask me for a refund, guys, if you don't know what to coordinate these at one time. Look at this one. That top is called long time pickup. Can you guys see that? Long time pickup. That you can run forever. And then right here, you're going to have the ground fault or long time delay. This point is called long time delay. Instantaneous pick is right here. And they use different values. 7 times the treb, 35 seconds at this point. That's what you do, guys, with this software. This point at the bottom is called limited, determined by the capability of the circuit breaker or the available short circuit. So, and all these are, look at this. If I have a 5,000 amp atom, I can trip within 0.005 second. If I have a 30,000 amp, I trip within 0.002 of a second. The higher the amps, at the bottom here, guys, amps, and at the top here, seconds or cycles. The higher the amps, the faster you can trip. You can adjust them, guys. Look at this one. This one, short time delay, 30 cycles. This is 6 cycles. You can move them. Move the instantaneous. That's what they call it, adjusting the instantaneous. We talked about, guys, tripping within 3 cycles. That's your wave. Fuse is the same thing, Adam. If you have a short circuit, look at that. Minimum melting time, 25 seconds at 200 amp. So if you have a fuse, what looks like, say, a 20 amp fuse, at 200 amp, it takes 20 seconds, guys, to start the melting process. And it will end the melting process within 120 seconds. So we'll take that, take a 20, I think it's 20 amp fuse. It will take a 20 amp fuse, 120 seconds to melt if you put 200 amps in it. That's what the time current characteristics give. Your time current characteristics give. If you look at this one, this is my ground fault. Look at here, 1,000 amp pickup ground fault. You can delay it. Time delay 0.5, meaning allow it to sit for 0.5 seconds. This one, if you drop it down, guys, it says no, trip at 0.1 of a second. Who cares? The longer you delay the ground fault, the more equipment will be damaged. That's it. So that's what we do when we do coordination. When you do coordination, guys, your curves, here's the main, look at this. This 1600 amp trip circuit breaker. Right underneath it is 800 amp. So Karen, wherever these circuit breakers are going to overlap, can you guys see that? This means all hell break loose and both of them will trip. Can you guys see that where they overlap? This means these two, and this range, and these two ranges, you don't have coordination. Can you guys see that? Everybody can see where they overlap. You don't have any coordination between these circuit breakers. So what do you do when you have circuit breakers like this? You move their curves away so they don't overlap. So if you have a short circuit within this range, you're guaranteed your circuit breaker, both of them will trip. That's what the coordination is, guys. You adjust these circuit breakers so they can play peacefully with each other, meaning the one closer to the fault will trip first. Derek, my friend, here's a fully coordinated system. Look how it looks like. Fully coordinated system, guys. Nothing is touching, basically. Can you guys see that? Everything is cool. So if I have a ground fault right here, the first circuit breaker, if you have it, guys, right here, the one that's going to trip is this circuit breaker. If you have a short circuit right in here, the one that's going to trip is this circuit breaker. And if you have it right in here, gentlemen, the one that's going to trip is this circuit breaker. That's fully coordinated system. Okay, they're not touching. When you guys, I can't emphasize, I want you guys to know that one when we go to SKM. When we do to SKM and say coordinate between the curves, that's what I'm looking for you guys to do. They're not going to touch in any way, shape, or form. Can you guys see that? Meaning they're adjusted time-wise and pickup-wise. So this circuit breaker, I don't know if you guys can see, no touching whatsoever. This means fully coordinated with this circuit breaker at the bottom here. Okay, you see that all the way, no coordination, nothing, no touching. And the last one is this boy here, which comes all the way. Um, that's what they call a fully coordinated system. Nothing. How do you do that, Adam? You grab a screwdriver and you start adjusting these settings here. Up, tweak, up, down. Here's pickup. You have long time pickup, no time delay, short time instantaneous. And you can adjust these by pressing the screwdriver. But which number are you going to put it at? These curves, guys, will give you numbers. When we run them at SKM, will tell you, oh, go put this dial at this number, at this dial at this number, to get you a fully coordinated system. Any comments, gentlemen? Any questions? Comments, questions about that? That's what coordination is all about. Here's another coordination between a circuit breaker and a fuse, guys. A fuse and a circuit breaker. Always ask yourself, Adam, are they touching? No, they're good. They're fully coordinated. If they're not touching. That's typically the same thing between a fuse and circuit breaker. So if I have a short circuit right here, gentlemen, this fuse will trip. If I have a short circuit right here, anywhere, this circuit breaker will trip. That's all. How do you achieve this? By selecting the proper fuse and the proper circuit breaker and adjusting them. The last thing that we have, guys, is fully coordinated with a ground fault. So we're going to be putting a ground fault in our system this time, guys. And I'm going to bring to your attention, Adam, and to the ground fault here. Look at, here's my ground fault. Can you guys see that curve? It's actually the ground fault at B, which is the main right here. Can you guys see that? That's the ground fault right here. And the one right underneath there is the ground fault at D, right here. Here's my ground fault at D. So I'm coordinated between the two ground faults, as well as between the three-phase, between the circuit breakers. Can I guys get you to understand that these are different things? The fuse is, and the circuit breaker also, can you guys see, this is the circuit breaker that goes with the ground fault here, is coordinating with this circuit breaker, with this fuse, that going with the second. Before I let go with this, Adam, I want you and Derek and Matt and Karen. These two red curves are one curve. The two red curves, guys, one of them just looks at the ground fault, the other one looks at three-phase. You guys understand? They are two things of the same circuit breaker. And the blue ones are the same. They are two functions in the same circuit breaker. One of them look at the three-phase. So this guy look at three-phase, short circuit. This guy look at the ground fault. That's all. They are the same thing. So we coordinate the ground with the ground and the three-phase with the three-phase. The same thing for the fuse here, guys. The fuse, the big guy is, what did we say, three-phase, short circuit, and the little guy is the ground fault for it. So when you have same thing in the same device, okay? So when you have a ground fault, what I'm trying to get to, when you have a ground fault, you coordinate ground fault with ground fault, three-phase with three-phase. You don't have to coordinate with a three-phase and a ground fault. You have to look at it, but typically ground fault with a ground fault, three-phase with three-phase, inside the same device. Any comments, gentlemen? Any questions? So that's basically what this chapter is all about. Fuses, a little bit about fuses, circuit breakers, and coordination. Karen, like I said, guys, in a couple of weeks, you're going to hear Chad talk about SKM and coordination and what's not. What we give you guys is the next level. I always say that, Adam, you can spend your time doing drafting, and that's fine with us, but this will take you to the next level to be a project manager, managing your own projects. At Mishad Cooley, guys, the ones who are running SKM right now, a bunch of them are graduates of this program. They're doing this coordination. So Nick is one of them, came here. He's one of the guys in charge of running short circuit for a project and coordination, not rocket science. We did it once in the commercial. I know that was the first time. I'm going to do it one more time for the industrial. So please read this chapter, read it carefully. Keep a book, and when you need it, if you ever need it, Karen, to do that one, review them. It's really not a whole lot of rocket science on it. Okay, so that's all what I have for you guys. Any comments, any questions? A couple of, sir. The rest of them is just a couple of. Here's look at this one. The wires coming out of circuit breaker. This is a shunt trip circuit breaker, guys. Different construction for circuit breaker to get rid of it. And that's basically what we have. Comments, questions, gentlemen? All right, so let's go and do power. So hopefully that will help you a little bit. Thank you.